Here's a combined loading question. Pause the video and give it a try. When you're done, compare it with me. My first job is to figure out all the force vectors, or the force directions, as well as moment. Moment is a big one, so we're going to start with moments. From statics, if you recall, that moment as a vector is just the cross product of r cross the force. And I can point a vector r from h to d, and I will get something like 18 in the x plus 10 in the j, units in inches, cross the force, which is just p, that's negative 150 in the k. Now you will do your cross product on your calculator or in whatever magical way you can think of, and you should get negative 1500 in the I plus 2700 in the j, units in pound inch. That's your m vector. Now I want to classify each element in this vector. So I look at the first one. That's m in the x direction. It's a bending moment. And here's the m in the y direction. That's actually a torque because you look at h, it stands tall along the y direction, and if you twist in that direction, it's a torque. So I'm not going to write my over there, I'm going to write t. I'm also just going to write mx is equal to negative 1500 pound inch. Torque is 2700 pound inch. And finally, the forces, which is just P, is negative 150 in the K direction, which is just 150 pounds actually. Okay, now we can find all our stresses from these from two moments and a force. And we're going to start nice and easy with bending. So you have your bending stress. That's in the x direction. It's equal to negative mc over I, which is now, if you look up, radius is 0.6 inches, and I here, it's a solid shaft or solid round. I is a quarter pi and the radius to the fourth. This will roughly get you 8,842 psi in a tensile direction, but I'm going to be lazy. I'm going to call that 8.84 ksi, kilo pounds per square inch. That's tensile. Now we look at the shear due to torque, which is in the y direction. That's Tc over J, which is 2,700 times 0.6. Now it's half pi radius to the fourth. That's roughly 7,958 psi, which I'm going to write as 7.96 ksi. This one doesn't really have a tensile or compressive direction. We'll leave it like that for now. Next, we'll look at P, which causes a shear stress or transverse shear. This is where I get a little lazy, so I already drew a graph that we can look at over here. Transverse shear varies as a quadratic function along the direction of the applied shear force, which is P. Let's call that V. And H just so happened to be at one of the corners where the transverse shear is absolutely zero. Very nice. If H was somewhere over here, I will have to calculate that, and it it would just be using the formula of, I think, 3 over 2 V over A. But this case, it's 0. So you can draw the graph or write it 0 or straight up write it 0. But keep in mind that if you don't justify it, it might be a little risky, but it should be fine. Okay, now I can write all of the force. These are all the stresses I have, and I can write sigma of H totally is just 8.84 KSI, and all the shear force at point H is 7.96 KSI. We can now draw the stress element. Start with a square and label which direction is which. Let's look at the shear graph again and notice the element H is along the XY plane. So I'm going to do that too. Say that's Y and that's X. Okay, now let's first look at the normal stresses. I have a tensile normal stress that stresses my element and tries to deform it like this. And shear, not very intuitively, is a torsion. Over here I have my element H, and that torque spins in this direction in the y-axis. What that's going to do to my element is deform it a little bit to the right, twisting it like that. What's the only way you can deform an element like that with a torque is somehow you drag it over there and you try to stop it from going over there at the bottom by dragging in the opposite direction. So I will draw my shear in these directions. And in the same way, I'm going to draw my tensile stress in that direction. And lastly, because this thing is in static equilibrium, you have to balance the forces by just drawing the complementary vectors so it stays that way. This part is just head points to head, tail points to tail, and you have it. Maybe label it as well. So the normal direction gets 8.84, the shear gets 7.96, and there you have your stress element in the current XY axis. Our next task is to find the principal planes and then draw the element in that orientation. So we're going to draw the Mohr circle and we're going to analyze it and we'll figure it out. First, let's draw the Mohr circle, line through it. The Mohr circle, by invention, has the x-axis cross through the center of the circle, and that x-axis is called the normal stress. We need 2 points that define the location of the circle. These 2 points, when connecting these 2 points, you will intersect the x-axis, and that will be the center of the circle. And these 2 points is y and x capital. How you find y capital is you just look at the y direction on the top, and you see 8.84 as well as 7.79, 7.96. And it's quite intuitive that up is positive, so 8.84 is the x coordinates. That would be the normal stress because we're plotting it on the Mohr circle. And what's not very intuitive is the shear stress. By convention, you have the stress element over here. Imagine that's the center of a circle. If the shear stress is trying to create a clockwise rotation, it will be positive. It's not very intuitive because in the past we always did counterclockwise as positive, but just remember Mohr circle is built different. So this element 7.96 is trying to create a positive rotation. We'll call that positive, so positive 7.96. And in the x direction, which is over here, there is no normal stress, so that's 0. And if you have one of them, you know the other one should be the opposite sign because they're pointing in opposite directions. But let's try to practice that analogy again. Center at H, this force, this stress over here is trying to create a counterclockwise moment or rotation. In the unintuitive way, that's a negative 7.96. Okay, now you have the two coordinates, let's plot it. The x-coordinate of point y is greater than the x-coordinate of point x. So y is somewhere over here, x is somewhere over here. And then the y coordinate of y is positive, so it's pick a random location somewhere here roughly. Then draw a line through the center of the circle, landing at the other side, and there you have the x coordinates. So x should be somewhere along here, which is, oh, let's write it here, x 0, negative 7.96. The x coordinate of x just happened to be 0, so I can draw a line through x, and then I will have my y-axis. Okay. Now I want to find the radius of the circle. There are formulas for it, but what I like to do is draw a vector from the center to maybe one of the points, say y. I always try to choose somewhere in the quadrant 1 or quadrant 2, but you do what you do. And that vector over here in orange will have an x component of exactly half of y, because sigma average over there is just the average of between 0 and 8.84, which happened to be 4.42, comma 0. That's a point. So y as a vector is equal to 4.42 in the I direction plus 7.96 in the J direction. Do the Pythagorean theorem, and I will get that R is equal to 9.10 KSI. Then I'll do my inverse tangent, and I'll figure out this angle here. That's by definition 2 theta p will be equal to roughly 61 degrees with 2 significant digits. Now I can also write a complement of that because I need two theta p's. So that's my other theta p. Why I chose that is because one at some point, some angle rotation, it will be over here. And if I rotate that 180 degrees, the xy coordinates will flip. And not the best explanation, but whatever angle you have here, you can just plus 180 degrees or subtract it by 180 degrees and you'll get the angle. So I'll subtract by 180 degrees because I don't like big numbers, and then I'll take the absolute value of it because soon I'll just label like which direction it should be rotating and that'll be good. That'll be 119 degrees. Okay, now let's divide that by 2 and try to actually figure out which direction I should be rotating. So I have a 61 degree divided by 2, that's 30.5 degrees. Okay, in order to get from my orange vector to the x-axis, I can rotate in the clockwise direction. So I'm just going to draw a clockwise symbol over here. And on the other side, I can rotate it counterclockwise by 119 degrees and get to the x-axis as well, but just pointing in the negative direction. So theta p2 would be, what's 119 divided by 2? 59.5 degrees counterclockwise. Okay, now in this question, they didn't ask me for the shear theta, so I'm not even going to bother doing them. And now I have the angles, I have my R. I'm still missing the maximum and minimum sigmas, so that's x max, because by looking at it, that's the maximum magnitude of sigma you can get, and that will be sigma min. Let me go back to my green. Sigma max, by looking at this graph, is sigma average plus the R, so 4.42 plus R, which happened to be 9.10. That will get you 13.52. Did I do that mental math correctly? Yep. Sigma min will be 4.42 minus R, which is 9.1, and that'll get you negative 4.86. Both are KSIs. Okay, now I think we have all the information to draw the rotated state or the principal plane states. What I'm going to start with is 0 degrees orientation. Draw my datum line kind of line so I can reference off of. Next, take out a ruler, if you even bother to use a ruler. Theta p1, I'm just going to draw that one state because the other just had the xy coordinates flipped. That's 30.5, which is roughly 31 degrees. So I'll set my ruler to that and draw a long line through. Take away that ruler. And draw a square on it. Not the best square ever, but it'll do. It will do the job. Roughly like that. Okay. Let's take out another color. Now, how do we label this? We do know that this rotated 31.5 degrees. The trick that I try to use is, here's y as a point. What I did in the Mohr circle sense is rotated by that many degrees, and then my y vector is suddenly there. Let's call that y prime. So y prime, recalling from my state that's unrotated, y is this direction. It's all this stuff over here, and x is all this stuff over here. So I know that even if I rotate it by a bit, the y is still roughly in this direction, but it's y prime now. So let's do that. I have the coordinates for y prime. So y prime is at sigma max and has 0 shear stress. Very nice. And I can just call that y prime direction, x prime direction. And I know my y prime as a sigma is 13.52. Does it have any Does it have anything on the x? Yes. Along this line, you will move to the other side of the circle, which will be your x prime. X prime has a coordinate of sigma min, x value, and no shear stress. So sigma min is a compressive force, stress. So it will take a form that roughly looks compressive. And what that value was 4.68. Yeah. Okay, now this is your translated H state. Is there anything else that needs to be done? No. So that's it for this video.